Thank you. So yes, today I'll be talking about cosmology, essentially, and in particular the issue of the Hubble tension and what might be causing it, but also a few other tensions for the standard cosmological paradigm known as the lambda cold dark matter or ΛCDM. So in particular, I'm going to be talking about like the idea that we're inside a local void and the evidence for that, and also about the peculiar velocities with outflows. So I'll get onto that towards the end of the talk. So what, roughly speaking, is the Hubble tension? In case you're not familiar with it, one of the most important cosmological parameters is the present expansion rate of the universe. So essentially, distances between unbound objects quite far apart, they rise proportionally to some scale factor A, which is a function only of time. And this dot indicates the time derivative. So the ratio between A dot and A is the Hubble parameter. And the value today of that is called the Hubble constant. So the zero substitute indicates the value today. Now, how can we get the H0 parameter? So one way to do it is if you look in the very early universe at the cosmic microwave background radiation, then what you see are these tiny temperature fluctuations at the 10 to the -5 level. And in order to try and fit them, in particular, exactly what is the typical scale of the fluctuation, the angular scale, and the whole sort of angular power spectrum. Using the ΛCDM model, you would need several sort of pre-parameters, and you can fit all of them. And you can get out of that, one of the fit parameters is the H0. So roughly speaking, this is like extrapolating the early universe forward to the present epoch. That is shown in this figure in the top part. So different measurements generally agree that the H0 parameter must be in a narrow range of values. And these are in kilometers per second per megaparsec. So this is pretty indirect. A much more direct way is to use the local universe and actually see how quickly it's expanding. So to do that, what you would do is you would measure the distances to galaxies or other objects like supernovae. You would measure their redshift, and you would then do a linear regression. The idea then is to get the slope of the linear regression between redshift and distance multiplied by the speed of light. That tells you the present Hubble constant. So this relation will curve if you go too far out. So the slope of the relation locally is the value of the H0. The bottom part of this figure shows all different sort of techniques to measure H0, and you can see they all cluster in a narrow range around here in this red band, which is distinct from the Planck value. So this is the Hubble tension. Now, one important thing to understand is the impact of local structure on the Hubble constant measurements in the local universe. So essentially, the local measurement is sensitive to nearby structures. So for example, the Andromeda Galaxy is approaching us. That is not because the universe is contracting. This is because there's additional motions on top of universal expansion. But it's thought that as you look at more and more distant galaxies, these so-called peculiar velocities, although they would remain the same typically, they would be relatively less important because the contribution of the expansion of the universe would be more important. However, if we are in a void, and we're sort of, in this case, our location is shown with green dot, and this void is expanding faster than the average because it's an underdense region, and that the matter is sort of pushed away from the underdensity. then the peculiar velocities could, well, rise as you go away from the void center, and then eventually start coming down as you go very far out. So it's possible that you would get a large region in which the apparent Hubble constant is larger than the actual value of A dot, the actual expansion rate. So in short, peculiar velocities might skew the local expansion rate measurement. There is actually a lot of evidence that something like this is going on in terms of galaxy number counts. So there have been various surveys to try and quantify the space density of galaxies, the number density in different regions of the universe at low redshift. So in this particular study used the near-infrared 2-mass survey, covered 90% of the sky, using sort of spectroscopic redshifts, and it went quite deep. It covered most of the luminosity function. So here, if you see galaxies have typically a certain absolute magnitude. So absolute magnitude is on the x-axis. And the y-axis is the percentage of the total luminosity of galaxies contributed by that range of magnitude. So the survey managed to cover like most of the luminosity function. So we have a pretty good idea of the total sort of luminosity emitted by galaxies in different regions of the local universe. And what you can see on the right panel is the co-moving luminosity density. The precise units aren't important. But the important thing to understand is that here, the measurements are all basically the same. So this presumably is the average value for the universe, average luminosity density. But locally, it's less. So this blue point corresponds to an average over this whole range. And you can see that the luminosity density is about half the cosmic average value. So there is significant evidence that we're in an underdensity. Now, we looked into whether such underdensities are likely in the lambda cold dark matter framework by considering 1 million vantage points on a grid in the Millennium SXL simulation. It's a large lambda-CDM simulation. It's the dark matter only, but you can get the mass, the stellar mass, using semi-analytic modeling. And what we've done basically is plotted the frequency distribution of delta, which is the density contrast, underdensity, because we were only dealing with underdensities primarily with positive delta is an underdensity. Yeah, the observations are shown here. The distribution of points in the simulation is shown in this blue histogram. You can see there's a significant mismatch at 6 sigma confidence. So the observations actually rule out the lambda CDM framework. This, by the way, is independent of the Hubble tension observation. So one thing that's been allowed for in this model is the fact that the density contrasts have been enhanced by a factor of 1.5 in the lambda CDM case, because observers think they're seeing out to some distance based on the redshift, but this is assuming a uniform relation between distance and redshift. So in other words, assuming like there's no void. In reality, because there is, the actual distance they're observing for any given redshift is slightly smaller, and therefore there's fewer galaxies in that region. So basically, that has the effect of slightly enhancing any actual void and make it easier for observers to detect. So what I wanted to explain, though, is the impact of such an underdensity on the Hubble constant that you get locally. So first of all, one thing that is quite clear by now is that local measurements of H naught should be pretty close to the correct value in lambda CDM. There isn't that much so-called cosmic variance. So this can't really be the answer in the lambda CDM framework. But we saw that we need to enhance the growth of structure in some way in order to explain the observed KBC void, which is being confirmed in many different other studies. This is like a more recent example. So what we did here is plot on the y-axis the underdensity, and on the x-axis the ratio between the local and the actual value of the Hubble constant. So this green dot shows what would typically happen on average is that the we would be in a region with average density. There would be no enhancement to the Hubble constant, no underdensity. But because of fluctuations, at 1 sigma we can be up here, and 5 sigma we can be up here in ΛCDM. So in a slight underdensity, there will also be a slight enhancement to the Hubble constant. However, the problem is observations are up here, and these also have uncertainties, right? But you can't explain the observations within their 5 sigma region, even if you allow for cosmic variance at 5 sigma. Importantly, though, the observations are such that a significant underdensity at like the 10 sigma level, in other words, a very large initial density fluctuation, could both explain the KBC void and the Hubble constant. Now, of course, statistically, this is not very likely. So what you would need to do is find some way to enhance the growth of structure such that this is not a 10 sigma event, but like maybe a 2 or 3 sigma event, and then it would be plausible. But you can see also that the KBC void and the Hubble tension both seem to be pointing in the same direction, and underdensity would naturally lead to a Hubble constant enhancement. So I'm going to explain now briefly about the MOND model that we use. So this is motivated by the rotation curve anomalies or the missing gravity that we see in disk galaxies. So disk galaxies have rotation curves which look like this. This is the rotation speed as a function of distance. This is the Newtonian expectation, and these are the observations. This is the usual situation in astronomy, right? The question is, how do we deal with it? Well, before we do that, we'll try and quantify the discrepancy in a slightly different way. So what's plotted on the y-axis is the gravitational field that is implied by the rotation curve, so v squared over r. And on the x-axis is the Newtonian gravity from the visible mass alone. This is the line of equality, and the observations, however, are up here. But this graph shows data not just from this galaxy, but from 153 galaxies. They all seem to follow this very tight relation, which is also present in the elliptical galaxies. So these lines in the background show the relation to the spiral galaxies. And these colored dots show ellipticals or S0 galaxies. And these ones show ellipticals. This one, by the way, is using gas as a tracer. Because some ellipticals have a thin disk of gas that's a very small percentage of the mass, but it's very useful. And here it's using like hot gas in the halo. With the spiral galaxy data in the background, the colored dots showing the data. So this radial acceleration relation is pretty widespread. Now, this leads to the idea of postulating a fundamental radial acceleration relation which goes through the data, essentially. So, in other words, assuming that what you saw in the previous two slides was not a coincidence. If it wasn't a coincidence, but it's caused by some fundamental physics, then what you can do is postulate that when the gravitational field is stronger than some threshold, the gravity is the Newtonian gravity, but when the gravity is weaker than threshold, it scales the square root of the Newtonian prediction. I won't go into too much of the details of MOND right now, but it's been reviewed in some detail here, at least as far as the evidence at that time was concerned. Unfortunately, the evidence since then pretty much rules out MOND on all scales other than the galaxies, including in particular solar system ephemerides. So from tracking of the Cassini orbit around Saturn, it's ruled out at 9 sigma confidence. Wide binary is ruled out at 16 sigma, and it's a serious problem in clusters. So what this shows is basically the MOND cannot be correct. However, what I will be showing the rest of this talk is a cosmological sort of model that uses MOND as a proxy for what could happen if you had a standard expansion history, but you enhance the growth of structure. So this is just sort of a motivation of, it's just a particular way to enhance the growth of structure in the universe. the actual way in which structure formation is enhanced could be different to MOND, but it could still be faster than in ΛCDM is the idea. So how do we do this? So by the way, this is all completely standard so far. You have equations of motion like this in general. So the acceleration is given by a contribution from the homogeneous universe between, so this is the distance between like the void center and some particle. It will accelerate even without any kind of inhomogeneities. But there's also an extra term caused by inhomogeneity, caused by the underdensity. This is the initial conditions. Basically, the mass deficit interior to the radius of the particle sources an extra outwards gravity. So that's why there isn't a minus sign here, because delta m is the amount by which the enclosed mass is less than the cosmic average. So the delta m is like this. This rho naught refers to the present density. You could also just use rho r cubed, where rho would be the density at the equality of constant. But either way, you need to subtract the ma, which remains constant with time for a particular trajectory, so assuming no shell crossing. Now, this is all standard stuff, so that's not going to solve the Hubble tension. What we need to do is enhance the outward push created by the same sort of mass deficit, and that is done in a way which is inspired by MOND, which is to add an extra boost to the GM. So that's essentially what we did. Now, what that does is it enhances the growth of structure. So delta is the fractional underdensity on a 300 Kelvin megaparsec scale. This is the cosmic scale factor, which more or less is proportional to the time. So in case you're wondering. Now these red lines show the growth of structure in the ΛCDM case, the Newtonian gravity, and the blue lines show what happens in MOND. So you can see that we're able to enhance the growth of structure significantly. The main thing is this isn't really sort of a prediction. It's more like a hypothesis that structure formation has been enhanced in some way. One obvious consequence, though, is that if you imagine a very significant initial underdensity, which grew to this amplitude today, in the Newtonian case, it would have started much smaller in the MOND case. Therefore, the growth rate would be much higher, even if the delta was the same in both models. What that means is that the same delta today is associated with a larger enhancement to the Hubble constant in MOND. In other words, for the same delta, delta dot is higher if structure formation is enhanced. Therefore, the peculiar velocities are enhanced. So that's just something to bear in mind. Now, one important thing to understand given what we talked about peculiar velocities, and given also that they might be much more significant than in ΛCDM, is that in general, redshifts of astronomical objects like galaxies, supernovae, are not purely cosmological. That should be fairly obvious by now, but there are other sources of redshift beyond the expansion of the universe. That is one of the terms. So the ratio between the wavelength at which you observe a spectral line and the wavelength at which it must be emitted is given by the inverse of the scale factor at the time of emission multiplied by an extra term related to the velocity of the source, the relative velocity between the source and the observer, and also another term related to the gravitational redshift. So if the potential here is different to the potential at the location of the emission. What is typically done is to ignore all this. If you're looking more than 100 megaparsec, we typically assume that it didn't matter. So what would happen if there was extra source of redshift is that you would think the A at the cosmic scale factor, the time of emission, was smaller than it actually was. In other words, you would like overestimate the redshift. There'd be some mismatch in the actual value of A when the photon was emitted and the value you think A had at that time. This would lead to some delta A, and the time evolution of this delta A would have an effect on the cosmological parameters. So in particular, if there was a time derivative of delta A, to reflect the Hubble constant. So you can do like a Taylor expansion of delta A. It's very hard observation to infer more than like the first two terms, which is why we've not considered beyond that. But what we did then is we fit the pattern of delta A predicted by a model to get the time evolution of delta A, but like as a parabolic fit. And then we found we added that onto the A dot and A double dot that you have at the background level. So that gives the A dot and A double dot that would be inferred by an observer in that model, which gives us like an estimated, like an observation analog for A dot and A double dot. The A dot directly tells you the Hubble constant that observer would see. The A double dot is used in this manner to get the so-called acceleration parameter Q0 bar. And as I said, observations can't really infer much more than these two. So you can try and infer H0 and Q0 bar by looking at the data on supernovae, which gives this observation here, along with some uncertainties. There's some covariance between the two. The main thing is, in the model, we're able to match that pretty nicely for, we considered 3 different density profiles for the void, and all of them work. The triangle is kind of hidden here behind the square, so these both consist at the 1 sigma level. The prediction of the ΛCDM model using the CMV data, so the blank prediction is here, which is in significant tension. But just this one data set alone is already 4.4 sigma tension. We can nicely solve the H0 and the Q0 bar problems. Indeed, there is a slight anomaly in Q0 bar being higher than the 0.53 predicted in ΛCDM. But it's possible. I'll just explain briefly that this model consists of slightly symmetric outflow from a void center plus some systemic velocity of the whole void due to even more distant structures, which will be important in a set for various reasons. I'll come on to that. So the velocity in the CMB frame is found by adding the velocity away from the void center with the systemic void velocity using the cosine rule. The void's been divided into cells. That's been done in each cell. These red cells kind of illustrate the part of the void where the local group, so Milky Way and Andromeda galaxies, their average velocity in the CMB frame is equal to the velocity predicted by the model in this region. So I'll come on to that in a bit more detail in a sec. So basically, this is the velocity field of our model. Right? Only the magnitude of the velocity in the CMB frame is shown. Those are the directions, they're roughly speaking away from this point. The model is axis symmetrical on the x-axis. The whole point is moving towards the left. Okay, so the velocities are away from here. This black contour shows all the points where the velocity essentially matches our velocity in the CMB frame. But when I say our velocity in the CMB frame, obviously should try and minimize the effect of Earth's motion on the sun motion on the Milky Way, and the Milky Way motion relative to Andromeda. We're using the local group as the largest reference frame to which you can reliably transform your velocities. Anything beyond that, and it becomes a bit dodgy. What exactly are the velocities? Because we know the velocity of Andromeda, but we don't know the velocity of even more distant galaxies in 3D all that well. But the main thing is that, we have to build this black contour for the model to work, okay, which is not that unreasonable. It's a reasonably significant fraction of the void, like a few percent of the void's volume. So our location of the void is not really fine-tuned, and we considered like a joint sort of look at the model prediction for the velocity of the observer in the CMB frame and the chi-square with respect to various other observables. And this is like the model prediction, which is up here, and 2 sigma could be out here. This is a 2.53 sigma contour. The reason that's important is the actual observations are up here. This is the actual value of chi-square and the actual like local group particular velocity. So you can see like it's not the model's got a fairly good fit overall. And if you want to see like exactly what are the different sources of tension, then we can look at that in the appendix in the question. But basically, there isn't that much tension overall. So now you might be wondering, like, can we test this model in a bit more detail? And we can using the so-called bulk flow. The bulk flow is a sensitive measure of the velocity field within the void. Now, one thing to understand is it's quite difficult to reliably test a model using the velocity field in the void because you measure the redshifts of objects, and the redshifts are partly due to cosmic expansion, partly due to the Doppler effect, due to motion, due to peculiar velocity. And these things are hard to disentangle. But they can be disentangled if you don't just look at one of them, you look at several objects in many different directions, because ultimately a local void would not cause a peculiar velocity rise exactly linearly with distance, whereas like a change to the A dot would basically have that effect. So there must be higher order effects, there must be anisotropy within the void as well, which I'll come on to. So this actually brings you on to the so-called bulk flow, which is the average velocity of all the mass within some region. Now, this isn't directly accessible observationally because we only have line of sight velocities, which we can consider as a vector. So when you measure the line of sight velocity of a galaxy from its redshift, you can consider this as a vector pointing along the line of sight, and you take the average of these vectors for all the galaxies in a certain volume. So you try and adjust the weights because you ideally want like every part of that sphere to receive equal weights basically. But if some parts have fewer galaxies, the galaxy in that part must be weighted higher to compensate for that. But otherwise, that's basically what we're doing. We're getting the average velocity in a certain region. But because it's using line of sight velocity components only, it's using only that component, if all the galaxies in a sphere had the same velocity, like the same vector velocity, then the bulk flow reported by observers would be 1/3 of that because of the projection. So that is something to bear in mind. Also, another crucial thing to bear in mind is that the assumed Hubble expansion rate has no effect on the bulk flow that's reported by observers, because even though peculiar velocities require you to subtract the Hubble velocity, and obviously H0 affects that, it does so in a spherically symmetric manner. Therefore, the vector average of all these 3D peculiar velocity vectors is unaffected by the assumed H0. So one thing that becomes apparent from the observations of the bulk flow, the bulk flow is obviously a 3D quantity, but I want you to focus on the total magnitude of the bulk flow, which is shown here as a function of the size of the sphere within which the bulk flow is measured. There is very significant tension with ΛCDM. Which is also kind of confirmed by another team subsequently. But basically, there is a serious tension with the bulk flow observation. So this was quantified by the authors and with chi-square analysis. Basically, there's a certain amount of bulk flow. The bulk flow along any direction should have a Gaussian distribution in ΛCDM with some variance that you can calculate, and therefore you can, if it's a 3D test, then you can work out a chi-square for 3 degrees of freedom. The thing is that there is more than 5 sigma tension. If you look at the likelihood of the bulk flow as a function of the scale beyond 230 H inverse megaparsec, there's a problem. So some people have argued that this is because in the early universe there was more power on this scale than expected in ΛCDM, which is why there's more power on that scale than expected today. However, this is not correct because if you look at the CMB on this kind of scale, there's no evidence for any kind of issues. This is a problem with the way structures grown in the millions of years after the CMB was set. And it's also not a problem at the background level. It's problem to do with structure in the universe. So what about our model for the bulk flows? So we considered 3 different void density profiles, and we also considered 2 different locations for ourselves in the context of each model. So basically, if I just go back quickly, we considered that we're either here or here, because we have to be on this black contour in order to have a velocity consistent with the local group peculiar velocity. But for simplicity, we consider the points on the x-axis, meaning there's two possible locations. So what is done here is all 6 combinations of void density profile of observer location are shown. The outer vantage point is shown with the dotted curves. That doesn't work. Okay, but the solid curves show the inner vantage point, and there with the maximum Boltzmann type profile in green, that also doesn't work. But the Gaussian and exponential ones work pretty well. So this was a study refereed by Rick Watkins in order to ensure that the comparison is done as closely as possible to the methods used by observers. Now you might be wondering, what about these gray curves? That is actually quite important. The thing is, when we constrain our location in the void using the local group peculiar velocity, I argue that that's the kind of largest scale to which you can sort of reliably transform like the sun's velocity. That is true, but ideally what you would want, right, is you would want the average velocity on a scale larger than the typical separation between galaxies, but smaller than the KBC point. The reason is our model doesn't include individual galaxies, right? It doesn't include small-scale features, irregularities in the velocity field, which means ideally you want the average velocity on a scale of several dozen megaparsec in order to constrain your location, constrain our location in the context of the model. Fortunately, we have this information because Rick Watkins provided us additional data points at low radii, which low radii for him, but still much larger than the local group size. That means that we can set our location a little bit closer to the void center, which would mean that we're able to match the first data point shown here. If you do that, obviously you're not guaranteed to match the rest of the bulk flow curve, but we do nonetheless achieve that. So the main conclusions that one can draw from this is that we are fairly close to the void center, because we tried, remember, vantage points which are close to and far from the void center, but the latter doesn't work. Also, the Gaussian exponential profiles have the void being deepest at its center, and these work well. But if you have a maximum Boltzmann profile where at the center of the void the density is the same as the cosmic mean, then it becomes underdense and then it returns back to the cosmic mean, which is a bit weird in some ways. But the thing is, we did try that out, and it doesn't work. It leads to the green curve. One other consequence goes to the next few minutes is the Hubble tension is supposed to only arise at low redshift in our model because we're proposing a local void. So what should happen is you should recover the Planck cosmology or the background cosmology if you look further out. That's one obvious consequence for local, for any kind of local scenario, certainly for local void model. Now, interestingly, that is what seems to happen according to Gia et al., but also according to a few other studies. Basically, what they've done is they've tried to infer H0, but only from the data within a narrow redshift range. They've also been careful to try and remove correlations between the data points. So these data points are essentially all independent, but they are different in, they're independent, but they're also different in the redshift range that the data come from. However, data in principle at any redshift could be used to infer H0, including at the CMB redshift, right? But it's not at redshift 0 at all. And you can see this nice descending trend where at high redshift the data is more or less consistent with the Planck value. But at low redshift, of course, you have this Hubble tension, which they've shown as a super tiny error part there. So clearly, there is evidence that at high redshift, the Planck cosmology is totally fine. The Hubble tension arises only in the fairly nearby universe. Also, one other thing, if there was a systematic calibration error with the supernovae, then you would just have like a flat line up here, which is not what you see. Okay, so this plot includes data other than supernovae, but there's a version of this plot in their paper which uses only supernova data, which looks similar. And there was this study which was published recently, accepted by the referee recently, which shows the same kind of thing, but in a different way. This shows the expansion rate at different epochs, so A dot by A, but at different epochs. According to ΛCDM, the Hubble parameter should have been higher in the past, according to this black line, but the reconstruction has been done in a fairly model-independent manner, as an independent of what exactly the functional form should be. It kind of looks like this. So there's been a deviation from the black line at late times or low redshift. There's also like a slight compensatory adjustment here, but this is not such a big deal. That's basically to try and preserve the angular diameter distances in the CMB looking the same. Because they haven't assumed that they're assuming that this is at the background level that the H is higher than it should be. They're not considering the possible impact of peculiar velocities on this. There's also other issues faced by early time solutions. So, for example, if you assume that the expansion rate has always been 10% higher than in the Planck cosmology, and find some excuse for why the CMB is still like not contradicting your model, the universe will end up younger because of the higher expansion rate, and that will then cause problems with the ages of the older stars and globular clusters. There's also various other problems that would arise. So basically, recent results favor a late time solution to the Hubble bench. And just one thing I want to go through briefly before I get to the conclusions is that we plotted on here the scale factor A against the look-back time T in ΛCDM, and in our model, but this blue model it doesn't actually show the AFT, it shows the apparent scale factor at each epoch based on the redshift, which is calculated including the peculiar velocity corrections. That leads to the blue curve. This blue curve is able to solve the Hubble tension. So just one thing to bear in mind, only a very subtle change to the expansion history can solve the Hubble tension, because the slope of the blue curve is 10% higher than the red curve at late times. So I just thought I'd show that, and also argue that because this blue curve tends back to the red curve fairly slowly, this leads to a problem with previous studies that try to look at whether we're actually in a local void. For example, the famous Kenworthy paper argued that this void model is wrong, but they assumed that we're exactly on the red line, that we fully recover the Planck cosmology when the redshift is greater than 0.1. In other words, the peculiar velocities become negligible beyond redshift 0.1, even if there is a void. Now, that's not how our model works. Basically, let me just, yes. What is shown on here in blue is a fractional enhancement to the redshift as a function of look-back time. And you can see that, okay, we get this nice 10% enhancement in this range, which is typically used to constrain H0, but the enhancement only decays away fairly slowly. So that's just something to bear in mind, that you get like a little bit of an enhanced Hubble constant even further out. Okay, so that's everything I wanted to say for this talk. So I'll just briefly summarize the conclusions, which is that galaxy number counts show that we are in an underdensity out to about 300 megaparsec or more, and there's evidence across the whole electromagnetic spectrum about this, causing significant tension with ΛCDM. This requires significant outflow given the initial conditions more or less homogeneous. We argued in this paper that, with some quick back of the envelope calculations, the local Hubble constant would be about 11% higher than the actual value because of this. But that will depend a bit on the model. The thing is, that's kind of what we observe with the locally measured H0 being larger than predicted. We were able to link the Hubble and local void tensions in a semi-analytic void model that I was showing earlier. The model was not constrained using bulk flow measurements because those didn't exist at the time, but the predicted bulk flow curve can be extracted from the model fairly easily and compared with observations. once they became available. And that led to excellent agreement for 2 out of the 6 combinations of void profile and observer location. So not all our models worked, of course, or not all the variants of the model worked. The other thing to bear in mind is that measurements at redshifts higher than half, approximately, are quite consistent with the background Planck cosmology, which suggests that the Hubble tension is caused by something that occurs fairly late in the universal history or fairly locally. Even people who have been working on the early time solutions to the Hubble tension for many years acknowledge that it doesn't really work for many reasons, including that the universe becomes too young in those models. And the last thing I want to explain is that we see lots of people have proposed various ideas for how the Hubble tension might be solved, but very few of them had a different sort of motivation. They weren't trying to solve the Hubble tension as such. Like in our case, we included the void because that's what you observe. And also, they made a successful a priori prediction of some phenomenon, which is unlikely ΛCDM. But according to the model, for the solution to the Hubble tension, it should happen. And then a few years later, the somewhat unusual prediction is actually confirmed. So this kind of scenario is actually quite rare in this field. So that's what I wanted to say. Thank you for listening. I think that's time for questions.
Thank you very much, Janelle. And yeah, we indeed do have time for at least 1 or 2 questions. I see we have a question from Philip online.
Yeah, go ahead.
Yes, hello, good morning, everyone. One of the things I want to ask is this.
Yeah.
When we look back at delta T over T, we're seeing a signal that is produced at last scattering, travels all the way to us, and then we measure. Now, you're now saying that at redshift less than 0.5, that signal gets modified. Now, it seems that the entire analysis of delta T over T would have to be modified and not just H0.
Oh, at late times, yeah, we looked into this a little bit. So avoided late times would not really affect the pattern of anisotropies in the CNV very much, right? What the main effect that we found that it could have is that we're sitting on a slight potential hill because we're in a void, and that affects the so-called monopole temperature of the CMB. Like all the photons get sort of redshifted a little bit, trying to climb up the potential hill. But this was a 0.1% effect, and given the uncertainties, like we argued in the Haslbauer et al. 2020 paper that this didn't really violate the observational sort of constraints. In short, a large local void would not substantially affect the pattern of anisotropies in the CMB, right?
Are you saying that it's really only going to affect small l, if at all?
It may affect small l, yes, because
Okay.
Yeah, but there was an analysis the CMB team did restricting to L less than 800, which gave much the same results.
Okay.
I see we've also got a question online from Tom.
Yeah. Okay.
Yeah, nice talk, Indranil. We of course been talking about this void for about 40 years, but it's nice to see, you know, Keenan, Badger and Carrie and yourself making good use of it. But the problem with it is that, of course, is for us was that we could say, you know, we've solved the Hubble tension, but then you immediately have to say you've got another tension, which is with lambda CDM, as you're pointing out, in terms of the size of the void. But if it's a 4 or 6 sigma deviation from lambda CDM, why don't we see this void, you know, in other places in the universe, which then would start to contradict the correlation functions and power spectra on few hundred megaparsec scales that are well measured in the lambda CDM model? I mean, you come to some awkward conclusion that this void is only a local void if you go that route, and then you're into non-Copernican models rather than and even the MOND thing that you're suggesting wouldn't solve that problem.
Well, first, okay, can I answer the second part of this first?
Yeah.
Regarding the idea of us being a non-Copernican observer. So first of all, clearly all observers are not exact, right? What has been argued is that our position in the void might be a little bit fine-tuned. But we look into this pretty carefully in terms of the local molecular velocity of 630 kilometers per second, which is a little bit low compared to the model, as in typically it's higher. But we argue that like a reasonably significant fraction of the void has a particular velocity of that or lower. Therefore, although we do need to be in a certain sort of location in the void, if you try to quantify like how likely that is, it's not that unreasonable that we'd be sitting in sort of this corner of the void.
But that's not quite the point I'm making. The point I'm making is that the spatial, the correlation function in power spectrum.
Yes, so I'll come to that bit in a sec. Yeah. So what you were saying regarding that if there was some mechanism to increase the density fluctuations enough to sort of overlap with observations, then we should see it in other ways. But there are other structures in the universe which are not consistent with ΛCDM and also suggest enhanced growth of structure. So for example, we did a detailed study on the El Gordo galaxy cluster collision and redshift 1, and the mass and the collision velocity are so high, redshift is so high, that is not consistent with ΛCDM. And recently, there was also a study which found this giant ring of galaxies on like a 400 megapascal radius or something, the diameter, which
the Gordo one I take seriously. I'm afraid I don't take the other one seriously. Roger Klaus at Preston has been going on about that sort of thing for a while, and they're not so well substantiated when you actually look at the data for his quasar. But anyway, I think you've encouraged me enough to go away and see if what I'm saying is actually true. If I can include a void of this size in a lambda CDM, large sort of scale cosmology, and not notice it in the power spectrum, because at 4 or 6 sigma you think you would, but maybe there's a way out.
Sorry, the thing I should explain is that the observations such as what I was showing here are relatively difficult further out. So if there are voids like this at larger distance, if there are voids like this further out, you would not be able to detect them in the same way by sort of measuring the spectroscopic redshifts of all the galaxies and counting the numbers in different regions. So further away, you probably have to use photometric redshifts, the voids will get blurred along the line of sight. So the kind of study done here is challenging further out, but there is evidence for the so-called Eridana supervoid, which is supposed to be in front of the CMB cold spot and might explain that. So there is some evidence for other voids, but to do a power spectrum, you basically need to do statistics of things like the KBC void on a quite large scale and look very far out, and then the observation will certainly not be possible to do in the same way. So I believe what you were saying towards the end of your point is correct, that if voids like this were reasonably common, they could get missed in kind of analysis you were talking about.
Okay, we are at the end of our slot, so I suggest we give Janelle a nice big round of applause at this point. And yeah, further discussion I'm sure can take place online if need be.
Thank you.